acupuncture, fascia, and myofascial therapy, toward a unified, mechanistic model. Fascia is no longer viewed as inert packing material. Over the past 2 decades, it has emerged as a richly innervated, mechanosensitive connective tissue network with measurable electromechanical properties. At the same time, research in acupuncture biology and manual therapy has begun to converge on a shared principle. When mechanical force is applied to collagen-rich tissue, whether through needle manipulation, acupressure, or sustained manual loading, it produces structural deformation that triggers cellular remodeling, purinergic signaling, ATP converted to adenosine, and modulation of nociceptive input. Anatomical studies show that acupuncture meridians frequently, though not universally, follow interfascial planes. Similarly, classical acupuncture points and myofascial trigger points demonstrate substantial, but not complete, overlap. Collagen piezoelectricity is a well-established biophysical phenomenon. However, available in vivo evidence suggests that neural and biochemical mechanisms account for the majority of clinically meaningful effects. Taken together, these findings support a coherent and testable framework linking traditional Chinese medicine, TCM, acupuncture, with Western myofascial therapies. Fascia has undergone a conceptual transformation. Once described as passive support tissue, it is now recognized as a dynamic, innervated system contributing to proprioception, nociception, and interoception. Parallel developments in acupuncture research and manual therapy have identified mechanotransduction within collagen-dense matrices as a plausible common mechanism underlying therapeutic effects. The purpose of this review is not to collapse distinct traditions into one another, but to clarify where the evidence genuinely converges, where uncertainty remains, and what experimental work is still required. By integrating anatomical, cellular, and neurophysiological data, we can move toward a scientifically grounded dialogue between TCM acupuncture and contemporary myofascial medicine. Fascial tissue, superficial, deep, and aponeurotic, contains a dense network of sensory innervation. Free nerve endings expressing CGRP and substance P, along with sympathetic fibers, have been documented in regions such as the thoracolumbar fascia and superficial fascia. Systematic analyses confirm that fascia participates actively in both pain perception and proprioceptive signaling. It is not merely capable of transmitting force, it is capable of reporting it. Collagen's piezoelectric properties were first demonstrated in bone and later extended to soft tissues. When mechanically deformed, collagen generates electrical potentials. While this phenomenon is robust under laboratory conditions, its functional contribution in living tissue appears modest compared to neural signaling and biochemical cascades. Clinically relevant transduction seems to depend far more on afferent modulation and mediator release than on large endogenous electrical currents. In practical terms, fascia is both a sensory substrate and a mechanically responsive medium, but its biological effects are driven primarily by neurochemical processes rather than by intrinsic electric fields. One of the most reproducible biomechanical observations in acupuncture research is the phenomenon known as needle grasp. As the needle is rotated, connective tissue winds around it, generating measurable strain within the extracellular matrix. This mechanical coupling induces rapid cytoskeletal remodeling in fibroblasts, an archetypal mechanotransduction response that can occur within minutes. Manual therapies apply comparable forces through stretch, shear, and compression. Although the delivery method differs, the tissue-level events are strikingly similar: matrix deformation, cellular adaptation, and altered interstitial signaling. Mechanical loading also activates purinergic pathways. Deformation of connective tissue increases extracellular ATP, which is enzymatically converted into adenosine. Adenosine, acting at A1 receptors, produces potent local antinociception in preclinical models, with emerging support in human studies. This ATP-adenosine cascade provides a plausible biochemical bridge between needling and hands-on interventions. Hyaluronan HA dynamics offer an additional layer of explanation. Mechanical input modifies HA viscosity and gliding properties between fascial layers, influencing perceived stiffness and movement quality. Cells involved in HA regulation, often referred to as fasciocytes, may contribute to this adaptive response. Thus, therapeutic benefit may arise not only from neuromodulation, but also from improved fascial glide. Do acupuncture meridians follow anatomical structures? Cross-sectional mapping studies indicate that many classical meridians align with interfascial planes. Biophysical measurements further suggest reduced electrical impedance along certain meridian pathways, occasionally corresponding to collagen-dense bands visualized on ultrasound. However, these findings are not universal. The most defensible conclusion is partial, non-random alignment rather than anatomical identity. Similarly, the relationship between acupuncture points and myofascial trigger points is substantial but incomplete. Early studies reported approximately 70% correspondence in pain syndromes, though subsequent debate has emphasized definitional variability and mapping methodology. Current evidence supports meaningful overlap without endorsing the claim that the two systems are interchangeable. Some authors have described fascia as a second nervous system. Such language should be understood metaphorically. Fascia does not generate or propagate action potentials. It does, however, function as a body-wide sensory matrix that interfaces continuously with somatic and autonomic pathways. Because it is directly accessible to mechanical manipulation, fascia represents a uniquely modifiable interface between the periphery and central processing. Needles and hands alter strain patterns, biochemical signaling, and afferent input. In doing so, they influence how the nervous system interprets tissue state. A coherent mechanistic sequence may be outlined as follows: mechanical input via needle manipulation or manual loading, connective tissue deformation with altered strain distribution and HA dynamics, fibroblast cytoskeletal remodeling and interstitial adaptation, ATP release and adenosine-mediated A1 receptor activation, modulation of mechanosensitive afferents and descending nociceptive control, clinical effects including analgesia and improved movement quality. These effects may preferentially propagate along interfascial pathways that often correspond to meridian maps and frequently coincide with trigger points, though neither alignment is absolute. It is scientifically reasonable to conceptualize acupuncture, acupressure, and myofascial manual therapy as fascia-targeted neuromechanical interventions. Clinicians may justify working along interfascial planes and at tender loci while acknowledging individual variability. Future research should prioritize high-resolution anatomical mapping, blinded concordance studies, in vivo biochemical monitoring during mechanical stimulation, and mechanistic randomized trials that match tissue strain across intervention types. The most consistent body of evidence supports a shared mechanistic core for TCM acupuncture and Western myofascial therapies, rooted in connective tissue mechanotransduction and purinergic signaling. Fascia operates as a densely innervated body-wide sensory network that can be directly influenced by mechanical input. Anatomical correspondences are meaningful, but not absolute, and collagen piezoelectricity likely plays an auxiliary role relative to neural and biochemical drivers. Framing fascia as a mechanically modifiable sensory matrix provides a disciplined and experimentally testable bridge between traditions, one that respects historical distinctions while grounding clinical practice in contemporary biological evidence.